Okay, hey everybody, it's now time to get started with the PE Exam Alliance, another night. My name's Andy Richardson and I'll be your host tonight. We're going to do a concrete problem tonight, and that is actually a structural or a breadth topic, so it is something you'll want to at least be somewhat familiar with for the exam. So what we have here is, it's just a number here, 315, but find the design moment capacity of the concrete beam shown. Okay, so this beam is 14 inches wide by 20 inches in height, as compared to not necessarily the depth, which would be to the reinforcement, but 20 inches high. It does have a dimension here given, 2.5 inches to the reinforcement, and it has number 5 bars shown, and we have 4 of them, so we have 4 number 5s, and it gives us the concrete specified strength and the yield strength of the steel. So we have enough information to find the design moment capacity. This is a condition where you have the size and reinforcement known, and you just need to know the design moment capacity. Pretty straightforward problem, really, and it's just a matter of understanding what to do and maybe checking a few things to make sure there's no curveballs thrown at you. Okay, so first of all, what we need to do is we need to find the dimension A, which if you know the formula for the nominal, okay, we have design capacity and we have nominal. Design capacity is phi mn, where phi is the bending reduction factor, phi b, and we need to know the mn, where the mn, the nominal moment capacity, is the area of steel times the Fy times the depth, okay, minus A over 2. Alright, so if we knew A, we have the depth, well, we have the height is 20, and the depth is just going to be 20 minus 2.5. It's going to be the depth to the rebar. Okay, so that depth will be 17.5 inches. So we have that information. And we have the area of steel, which is 4 number 5s, and number 5 bar is 5/8 inch in diameter, and it's also 0.31 inches squared. If you didn't know that, you could just do pi d squared over 4 and get that, so that's fairly straightforward as well. So that's 4 bars at 0.31 inches squared times the yield strength of the steel, which is 60,000 psi. You could use KSI there if you just kept your units straight. And then we have the depth of 17.5 and minus A over 2. Now that's the piece of information we don't have yet. The A is basically the amount of concrete. There's kind of an imaginary value here, and that's the amount of concrete that is effectively being used in the compressive portion of this, and it's set equal to the tension. And so we kind of need that value A in order to compute this. And people a whole lot smarter than I have determined and kind of set this information equal. But by setting the tension steel equal to compression, they're able to compute this A value, and it is equal to the area of steel times the yield strength over 0.85 times the specified strength of concrete times the width B. Okay, and plugging in the area of steel, which is still 4 times 0.31, and the 60,000 psi for this steel, and then 0.85, and then 3,000 was the given amount for the specified strength of concrete, and the width was 14 inches. So I get A of 2.08 inches. Okay, then that A, just plug that in up here. So essentially what we're doing is we're taking this moment arm and multiplying it out. And that moment arm is what we're trying to find. There. That's your moment arm. So you find that moment arm, or you multiply that moment arm times the tension, which is steel times yield strength. And I get the nominal, and that's M sub n without the fee, is 1225 inch kips. Divide that by 12 inches per foot. Typically you're going to find the concrete strength in kip feet or foot kips. So that's 102. Dividing that number by 12, we'll get that in 102.1 foot kips. And that's the nominal capacity. So the fee Mn, we're going to assume it to be 0.9 to begin with, and then we can validate that, or if we were in a rush we would just assume it to be 0.9 and go on with it on the exam. So we're going to assume that to be 0.9, multiply it by 102.1, and they may give us a clue on the exam like that too, to say it's 0.9. So we multiply that out and we get 91.9. And that's foot kips. And again, that's based on the idea of assuming the 0.9. We would want to validate that, and to validate that, actually, let's see. Oh, well, here's a little cleaner of what I just worked through. But let me see if I can give myself a little bit more room to work. Here we go. Here's just a whiteboard. So what we want to do is we want to validate the phi sub b is equal to 0.9. In order for that to be true, the strain has to be greater than the steel strain has to be greater than 0.005, and we can actually calculate that. The strain is kind of like the idea that the amount of stretch or movement of the steel inch per inch, if you recall that, and that's just equal to the strain of the concrete times, and we want to set that equal to 0.003 times the D minus the C over C, and that value C is equal to A over beta 1, which the A was 2.08, beta 1 is equal to 0.85 for F prime of C less than 4,000. So that C value is 2.45. You can see why I assumed it to be 0.9. This is actually a little almost as lengthy as calculating the problem itself. So then we take EC assumed at 0.003 for concrete, the strain of concrete is, and then the 17.5 was the depth of from the top to the centroid of the steel, and we subtract off the C value of 2.45 and divide it by the C value, and so we find the strain in the steel is actually 0.018, which is greater than the 0.005, and so our assumption was correct. Alright, so that might save you a minute to assume that and come back to it. The caveat to that, of course, is it could be that is if this value is not greater than 0.005, then the bending, that phi, becomes less than 0.9, and that could throw off the final answer as well. So the other thing you'll want to do is you want to check your rho min and rho max, particularly if you had a design problem, but since this is given the amount of steel, unless there's some kind of answer such as it's no good or something like that, then you would not need to go through the process of checking the rho min and rho max.